Thank you very much. I'd like to acknowledge my close collaborators and co-authors who are here in the audience, James Graham and Michael Fitzgerald, and also Mark Clampin, who's at NASA Goddard. And so my talk will consist of our latest results concerning Fomalhaut B. So it's a major update to our understanding of the Fomalhaut system. This next slide is a brief introduction to the system. Fomalhaut, the star, is a 2 solar mass star with age 440 million years. It's very close by. This is an A3 star, actually. The debris belt has been imaged at multiple wavelengths, and its semi-major axis is 140 AU. In the optical with the Hubble Space Telescope, back in 2004 and 2006, we detected one of these boring common proper motion companions point sources in the optical. And this is Fomalhaut B. Because it was detected in the optical, some of the ideas concerning its optical luminosity are that we are seeing reflected light from dust surrounding a planet, like a circumplanetary ring or a dust cloud produced by the collisional erosion of irregular satellites. However, Fomalhaut B has not been detected yet in the infrared. So that gives us an upper mass limit to the underlying planet of 1 Jupiter mass, roughly, and also has created some controversy that perhaps the optical image that is seen with Hubble is spurious. So maybe my talk is about nothing at all. Who knows? I hope to convince you otherwise. In the last 8 months, 2 independent groups from us, Galichet et al. And Curry et al., downloaded the Hubble data upon which this discovery was based, and they independently confirm the existence of Fomalhaut B as a common proper motion companion in the optical Hubble data. So our new data and the new paper that's out on AstroPH discuss our latest data set with the STIS chronograph obtained in 2012 in 12 HST orbits. And here is our 4th epoch detection of Fomalhaut B and the dust belt. So Fomalhaut B is confirmed yet again in a 4th observation, and I think the consensus view now is that it is indeed a real object. We have 3 independent research groups analyzing 4 epochs of data. So what about Fomalhaut B's orbit? Here's the 2004 position. Here's the 2006 position registered to the star. Here was a 2010 observation made with STIS, and here it is in 2012. So this westward motion is now confirmed. This trajectory is going towards the dust belt. So this talk will be about our analysis for the orbital elements of Fomalhaut B, and also I'll talk about 2 new features in the dust belt, this halo, this faint halo of scattered light and an azimuthal gap here. And taken together, I think one of the take-home points will be that Fomalhaut B is clearly more dynamically complex than previously envisioned. Are we confident about this westward motion towards the belt of Fomalhaut B at these 4 epochs? Well, one of the tests is to look at a background star. There's a single background star that's visible at all 4 epochs, and when you do astrometry on the background star, it nicely fits the parallax and proper motion that you would expect for a background star. James Graham has developed a Markov chain Monte Carlo method for sampling the posterior distribution of the orbital elements. Here are a sample of 100 orbits drawn from the Markov chain for Fomalhaut B based on this new astrometry in the sky projection. Let's take a look at these orbits in the face-on view and the edge-on view. This black dashed line represents the boundary of the belt. And here are the orbits. These dots represent the ascending and descending nodes. So our main new result is that the orbit of Fomalhaut B is confirmed to be highly eccentric, 0.8, plus or minus 0.1. The semi-major axis is comparable to or slightly larger than that of the main belt. And this brings up a very interesting new finding. Fomalhaut B's periastron now is much closer to the star than previously thought. The periastron now is in this tens of AU region where we would expect planets to form. Does Fomalhaut B actually intersect the belt? Is it coplanar with the belt? Let's take a look at one of the figures. Here is the posterior distribution and the cumulative distribution of the mutual inclination. The Fomalhaut B's mutual inclination with the belt plane is 17 plus or minus 12 degrees. Another remarkable finding from the analysis is that apsidal alignment is also indicated. The longitude of periaps for Fomalhaut B is shown in this distribution. It's 178 plus or minus 18 degrees measured counterclockwise from north. And this dotted line represents the periaps, longitude of periaps of the belt. Let's take a look at the belt now. I've rotated the image so that the major axis is on a horizontal direction, and I've binned the image along the minor axis, and the purpose is to emphasize the low surface brightness nebulosity here. And we can see that the belt is now detected to at least 209 AU, significantly farther than previously assumed from scattered light images. And in fact, the belt may go out to the edge of the field beyond 276 AU, where in this region the belt appears possibly perturbed, warped, and perhaps clumpy. This has to be confirmed. We also have now in the deep projection of the belt, we can take a look at aperture photometry along the azimuth of the belt. So starting from here, going counterclockwise, this is the aperture photometry. And here we measure dust depletion, or an azimuthal gap. It's not totally empty. It's about 50% of the light that you'd expect from the opposite side. And if you fit a polynomial to this gap, the size of this gap has a full width half max of approximately 50 astronomical units. So this sketch summarizes the results I just showed you, plus other results from the literature on what we know about the Fomalhaut system. The main belt isn't the only belt. There's an inner belt detected with Spitzer, studied by Carl Stoppelfeld and more recently by Kate Su. This 10 AU belt is near the ice line of the system. VLTI and Keck interferometry have detected a very hot disk close to the star. There's a clump of emission here, which is roughly 180 degrees away from the main belt. This was detected at 450 microns with SCUBA, and we have a program to perhaps confirm this with SCUBA 2. And here is the eccentric orbit of Fomalhaut B. So what has created Fomalhaut B's high eccentricity? Planets don't form on highly eccentric orbits. So in this notional sketch, we can hypothesize that this is a multi-planet system, that there perhaps is a Fomalhaut C, which is responsible for sculpting the inner edge of the belt, and possibly had a dynamical interaction with Fomalhaut B, scattering it inward. Or perhaps there's a Fomalhaut D closer to the star, which scattered Fomalhaut B outward. And maybe there's another planet proposed by Bowley et al. To explain the ALMA data. Maybe there's something exterior to the system as well. So what happens in the case where Fomalhaut B is scattered in? This type of orbit resembles the orbit of our centaurs, some of our eccentric centaurs. The eccentric centaurs in our solar system cross the orbit of Neptune. That means that the orbit is dynamically short-lived. So in fact, Fomalhaut B on such a planet-crossing orbit is a short-lived orbit. And possibly indicates, if it's a centaur analog, that it's a very low-mass object indeed. So to sort of estimate the lowest mass that Fomalhaut B might be, you can ask the question, how massive does the object have to be so that it holds on to its circumplanetary cloud and survives tidal forces during periastron passage, during periaps. If the cloud is too large, material, loosely bound material gets sheared away during periaps. And when you look at scaling the mass, to hold on to a cloud of sufficient size, Fomalhaut b would have to be something like a 5 times a Ceres mass, or roughly a dwarf planet mass. So that's possible. How about if Fomalhaut b is a planet mass that has been scattered out? This is a familiar story for the exoplanet community because radial velocity detected planets, when you look at the eccentricity distribution, there are eccentric radial velocity detected planets of order 0.8. And the literature, starting from about 10 years ago, has discussed planet-planet scattering events. And in this case, I'm showing work from Chatterjee et al., where you have 3 planets. The evolution, this axis here is years, so this is a very fast evolution. You can see the evolution of these 3 planets in terms of semi-major axis and eccentricity. The interactions can be chaotic, so that in fact the inner planet, let's take a look at this black line, will end up being the outer planet and evolve to high eccentricities. Well, if you have a planet mass now for Fomalhaut, wouldn't it destroy the belt? Well, answering that question depends on what that mutual inclination is, what you assume the mass of Fomalhaut b to be, and how long this configuration has been in existence. So in some of these models, preliminary models, dynamical models, we find that, in fact, if you have, in the specific case that I was testing, I have an interior nested Jupiter and a Fomalhaut b of a variety of masses. The problem is these simulations don't last for more than 1 million years because eventually, this is the coplanar case, Fomalhaut b's orbital elements get perturbed by an interaction with this nested Jupiter. But essentially, you can have a Neptune mass coming into and out of the system in the coplanar case without destroying the belt, and this can last for several 100,000 years. If not in the coplanar case, here is the case where you have an inclination of 20 degrees. Again, there's an interior Jupiter. Fomalhaut b is approaching the belt above its plane. It's crossing through the plane near its periastron and leaving the system below the belt plane. So Fomalhaut b in this simulation with a 20-degree mutual inclination never sees the belt or that Jupiter mass planet located at 120 AU. Okay, so take-home points. First, Fomalhaut b is real. So that means my talk was about something. And that's the only take-home point I have, actually. It's small. You can put it in your pocket, go home. But if you have a backpack, you can put these points in there. We have 8 years of Hubble imaging. We know the orbit is very eccentric. The belt crossing is in projection, so we don't know if Fomalhaut b will actually pass physically through the belt. Periastron now is at 32 AU, and overall we're observing Fomalhaut b at a very interesting time. 120 years ago, it had its periastron passage, and in 20 years, it's about to go through the belt, possibly. The mass limits are poorly constrained, something between a dwarf planet and a Jupiter mass. The belt can survive planet crossings, and there are mysterious new features in the belt that require explanation. And we're left with many interesting questions. Is Fomalhaut b an example of a planet-planet scattering event that we are witnessing? Why is it apsidally aligned with the belt? And finally, where is Fomalhaut c? Thank you very much.
Thank you for that great talk, Paul. Do you have any questions? Yeah, right at the back there.
Hello, Paul. Thank you for your talk. It was very nice. I had just two questions. If Fomalhaut B has been scattered by the planet, I don't remember, C or D, the one inside, right in the middle of the ring, did you put a minimum, do you have a minimum mass for this planet, and can we detect it in the images?
No, because by simulating this planet-planet scattering event. By the way, this is work to be done by follow-up papers to explore the parameter space more clearly. But because the mass of Fomalhaut B is so poorly constrained, let's say it's a dwarf planet, then why not scatter it outwards by, I don't know, a Saturn? But you do need a massive planet to scatter objects to high eccentricities. Something, a Saturn to Jupiter mass, I believe, would be right. Now, the direct detection limits, though, the limits for a Fomalhaut C so far are at about the Jupiter mass and above. So I think future advances and deeper imaging may, in fact, detect Fomalhaut C.
Okay. And my second question is, do you see any extension in the image?
So yes, that's a good question. We talk about it in our manuscript, if you noticed in that image I showed of Fomalhaut B, it's extended along the radial direction. And we do a test where we inject point sources into the image, which is contaminated by speckles, which are also extended. And it's not clear if that extent we see on Fomalhaut B is instrumental or caused by speckles, or if it's a real feature. And this is something we would like to confirm with follow-up observations. So if we see this extent in multiple epochs of observation, then we would have some confidence it's real.
Michael Liu, University of Hawaii. You're in kind of an unusual range, usual part of parameter space for fitting an orbit, in the sense that you have sort of a 10-ish year time base on a thing that has a 2,000-year period. So you've got less than a fraction of % of the orbit. And even for MC orbit fitting type things, it's kind of strange. I was wondering if you could comment a little bit more about the reliability of the orbital parameters, and in particular also their uncertainties. That's, I guess, and then a sub-follow-up is that, of course, fitting the orbit as well should provide a constraint on the mass of the star, and I'm wondering if that gives a plausible answer.
One nice thing is that the Grenoble group, Hervé Buste, has developed their own MC code for orbit analysis. We've seen it in their Beta B papers. We sent them our astrometry, just the astrometry, and they derived orbital elements that agree with our results. So this is their own separate MC code, and they're preparing a paper that would compare and contrast our results to what they have. But we don't have a mass determination by studying the orbits. The mass of the star actually has an uncertainty in its mass as well. It's 2 plus or minus 0.02 solar masses, something like that. Yeah.
Okay, Rosemary. Just wait for the mic.
Did you consider a stellar flyby? Have you considered a stellar flyby?
Yes, the question is, have we considered a stellar flyby? Yes, we have. So the Fomalhaut B is even more complex than, the system is even more complex than I'm telling you, because I didn't have time to show this slide. So there's a K-star here, TWPSA, which is 57,000 AU from Fomalhaut capital A. And here is the orientation of the dust belt is here, so Fomalhaut's dust belt. And here is Fomalhaut B, which appears to be a common proper motion companion with Fomalhaut A. So we know almost nothing about the orbit of Fomalhaut capital B. Capital B. And in fact, just for fun, I did some simulations where I have Fomalhaut B being scattered by this Fomalhaut C. And in this simulation, here's Fomalhaut capital B, TWPSA. A Saturn mass has now been kicked out to 3,000 AU and will continue to evolve outwards. And in fact, in some simulations, it will interact with either the center of mass, which is somewhere here, or will actually interact with Fomalhaut B, but capture is very unlikely.
Yeah. I'll just make a quick comment too. You said that you need a decent massive planet to scatter this thing. Mm-hmm. But actually, you don't have to have close encounters to get something to arrive at 0.8 eccentricity. It'll just, do a random walk out. So,
yes,
you see what I mean? So
if you think about it, if I'm telling you that the mass of Fomalhaut B could be a Ceres mass, then the mass in the belt itself is greater greater than the mass of Fomalhaut B. So the belt itself can also perturb Fomalhaut B in the low mass regime. And there's some studies about secular effects that would pump up the eccentricity.
I think we had a question at the back there.
Yeah, Paul, in the discovery paper, you discuss this possible photometric variability at blue wavelengths. What does the new data say about that?
So the question is Fomalhaut B variable? And in the test where I inserted point sources onto the speckle noise that I just mentioned this a few minutes ago, you can also conduct photometry. The resulting photometry gives an uncertainty of 35% in our photometry due to speckle noise. So I cannot confirm the variability. I cannot right now.
Okay, I think we have time for one last question from over there.
So you constrain the mass of Fomalhaut B to a Ceres mass based upon not allowing it to tidally disrupt. But why can't we let it tidally disrupt and explain it as a tidally disrupted comet? Can you comment?
So could it be just like a Shoemaker-Levy 9 comet that has been disrupted? And that's also possible. But that means we've recently seen, for example, Comet Ison, is that right? Comet Ison may not survive its periastron passage. Some comets barely survive and come out disrupted. It can be tidal forces, thermal breakup, spin. Spin will break up comets or weak bodies in our solar system. So there are other possibilities, and that would suggest that, in fact, we're very lucky to have observed Fomalhaut B now because it's in the process of dispersing. It's not ruled out, I think.
Okay, well, let's thank Paul again and the rest of today's speakers.